Buffer is the memory object for passing large data structure to OpenCL kernels. And it's the very straightforward object that we commonly use in an OpenCL program. It is a contiguous sequence of elements similar to a C array. Although you don't have to have an array, you can have your own defined data structures in this 1D contiguous space. And based on the memory flags we just described, depends on which one you use, a host pointer can be optionally supplied if we want to initialize the buffer with the buffer already on the host side. Or even we can provide the storage on the host side for the buffer. By default, OpenCL does not specify the physical storage for the buffer allocated. It simply says the data is in global memory. So this is the OpenCL create buffer APIs called CL create buffer. It takes the context as the argument, and also you can supply the memory flags, and then you can specify the size of the buffer, and optionally you can provide a host pointer if you want to use the pointer as a way to find the initial value of the data. This buffer does not return an event, instead it returns an error code and of course the buffer object. Let's take a look at a concrete example. The following code is to create a buffer that is read-only and initialize it with data from a host array. Let's assume that context is a valid context. At the very beginning, we declare the error code, and then we define an array A that consists of 16 integers. The CL create buffer will use, in this case, CL memory read-only. That is to say that the kernel can only read from this memory object. Also, it uses the option CL mem use host pointer. So when it says use host pointer, this is to say that this buffer will be allocated on the host side at this time, and we will see how the devices will get the values when it attempts to read the buffer. And after that, we will do an error checking to see if this create buffer operation is successful or not. Now we're going to look at a different example. This case, we are creating and initializing a buffer in host memory. And the memory flags we're going to use here is CLMem copy host pointer, and coupled with this host pointer that points to some space on host memory. These two options is to ask the OpenCL runtime to create a new allocation for buffer and copy the data provided by the host pointer. Note that this API does not generate an event. We can assume data copy is complete when the API returns. So the API we're seeing here is we're going to use CL create buffer, assuming we have a valid context, and this is the memory flag we're going to use, copy host pointer, and data is assumed to be the host pointer that points to some space in the host memory. What we see in this diagram is that this is the context we are performing this buffer creation operation. And because this is a CL create buffer API, and the goal of this API call is to create a memory object that is called buffer. And this memory object is going to be in a global memory that is accessible to all the devices. Because we have this CLMem copy host pointer flag, so what the OpenCL runtime does is to allocate a space that in fact resides in the CPU memory, the host memory. And because we supply the pointer data. So this API call actually then copies the data from this space pointed by data to the memory buffer just created. So we can see that we have implicitly a memory copy operation that's going to filling this new buffer with the data here. At this point, we actually don't have anything that's available in the GPU memory physically to be accessed by the compute units. So by the time the OpenCL kernel attempts to use this memory object, we will first set the kernel argument, then we use CL enqueue and derange kernel to instantiate the kernel, which will subsequently access the data. Only at this runtime, OpenCL will perform a DMA, direct memory access operation, to copy the actual data from the host memory to the device memory on the GPU side. And after that is done, the GPU kernel will then start reading the data from this GPU memory. So the point is the data transfer is implicit from the host to device prior to the kernel execution. After the computation is done, then we are going to copy the data back from the device to the host. So on the host side, you see another API, which is the CL enqueue read buffer, attempts to copy data from this memory object buff to the data buffer on the host. So at this point, there will be another direct memory access memory operation that copies the data from the GPU memory to the CPU memory. Or if it is FPGA, then it's the FPGA side memory unit.